Well, hello and welcome again to our journey into number theory, and we've been looking at the very famous Riemann zeta function, and we finished up deriving the so-called functional equation of Riemann, which is a remarkable formula that connects zeta of s to zeta of 1 minus s. And so this enables us to analytically extend the zeta function across the whole complex plane with some simple, with a simple pole at s equals 1, as we've seen before. So this line s equals 1 somehow splits up the complex plane in terms of the Riemann zeta function, and we get connections between what's happening each side by this lovely functional equation. Now the question one wants to ask is that, is this zeta function ever zero? When is the zeta function 0? And we can see that it's going to have some trivial zeros when s, from here we can see if s is an even integer, then we're going to get multiples of pi, and so we're going to get sine of that's going to give me 0. So we're going to see that at the even integers, even negative integers, we're going to get the value 0. What I want to show now is that the zeta function itself in the complex plane is not 0 anywhere over here. That is, if the real part of s is bigger than 1 anywhere in the complex plane, this is never 0. Now there are many little proofs of this. Some of them more complicated than others. I've come up with this one, which is probably well known, but this is a very simple demonstration that it can't be 0 there. So I'm going to take firstly s real, s bigger than 1, and you'll recall this lovely formula here, which we actually used to define the Möbius function. So if you take the Dirichlet series for 1 over the zeta function, then this constructed this multiplicative function mu of n, the Möbius function. Now by analytic continuation for s complex, we can also write this same formula down now, and this will be valid for the real part of s bigger than 1, where everything will converge. And I can take the modulus of both sides now, and so that's the modulus of this sum. And then I can use the triangle inequality here to say that the modulus of mu of n is less or equal to 1, in fact it equals 1, or is 0, so less or equal to 1 over the modulus of n to the s is n to the sigma, where sigma is the real part of s. Now this is all back in the real world again, and so these represent sums of positive numbers, so they're positive. We know it converges if sigma is bigger than 1. So this sum just equals some number, I'll call it a, but a has to be positive. So when I take the reciprocals then, I get the modulus of z then has to be bigger or equal to 1 over a. And that again is just a positive number. So that means this thing here cannot be 0 if the real part of s is bigger than 1. So that's a nice little proof there that zeta of s is not 0 if the real part of s is bigger than 1. Now this brings us then to the so-called Riemann hypothesis, which is this big result in, or big question in both analytic number theory and in it has implications in lots of different parts of mathematics, and it remains a very mysterious and very difficult unsolved problem that people have been working on for quite a long time without much success. Anyway, so we can see from the functional equation I mentioned before that zeta of minus 2n is 0, that is at all of the negative even integers, so at minus 2, minus 4 and so on, the zeta function takes the value 0. These are called the so-called trivial zeros of zeta of s. These, as I mentioned, arise from that sine term in the functional equation. Now I've just shown that the zeta of s is not 0 if sigma is bigger than 1. So the functional equation then tells me that if the zeta of s can't be 0 if sigma is less or equal to 0, except for the trivial zeros. So there are no zeros across here, except for the trivial ones. There are no zeros across here. Not too sure about what happens along here yet. We'll get to that later. And I want to now just very quickly show that there are no zeros along this real axis here between 0 and 1. And we do that by simply observing that this particular formula that we derived earlier, that if s is real now and s is bigger than 0, then we saw before we could write zeta of s as s on s minus 1 minus s times this integral involving the fractional part of x. So taking zeta minus this and taking the absolute value of this, because s is real now, this is less or equal to s times this integral, and I can replace the fractional part by just saying it's less than 1. And this improper integral, of course, just converges to 1. So unpacking that inequality, then I have zeta of s is bigger than minus 1 plus s on s minus 1, and less or equal to plus 1 plus s on s minus 1, which is 2s minus 1 on s minus 1. So if I take s between 1/2 and 1, so that means I'm taking my s in this little region here, s real, then you can see that both of these terms are negative. So that means that zeta of s is negative for all s in here, and then using the functional equation plus the fact that zeta of 1/2 is not 0, which I'll get to in a second, then we're going to have zeta of s is negative if s is real in between 0 and 1. We'll soon show that zeta is not 0 on the line 1 plus it either. That is, on this line here, zeta is not 1 either, sorry, is not 0 either. So hence zeta is nowhere 0 outside of what we're going to call the critical strip, except for the trivial zeros. And nor is it 0 on the real line in the critical strip. So this region in here is known as the critical strip. Now I said I would just show that zeta of 1/2 is not 0, so I'll just quickly shove that in here. That comes out fairly quickly actually. I'm going to use this formula we saw before. This was one of the analytic continuations of zeta we saw before, using this alternating zeta function here, and we saw there was a factor of 1 minus 2 to the 1 minus s inverse out the front connecting the two. So if I plug in 1/2, then this factor at the beginning just becomes 1 on 1 minus root 2, which by the way note is negative. And I just write the terms of this series out, so it's 1 on root 1 plus minus 1 on root 2 plus 1 on root 3 minus 1 on root 4, and I'm going to bracket them in pairs. And of course it's easy to see that each of these brackets, these all represent positive numbers, so I have a sum of positive numbers in here multiplied by this negative, and so this is strictly negative. So zeta of 1/2, whatever its value, it certainly is not 0. So that completes that part of it. So just to recap then, in the complex plane, the zeta function is never 0 over here except for these trivial zeros. It's never 0 over here, and it's never 0 along here, and later we'll show that it's never 0 along this line here. At 1, of course, we have a simple pole. Now we can take this functional equation I mentioned before. The functional equation is remarkable, but it does look rather cumbersome, and what Riemann did was he tried to write it more compactly to try and see a little bit more clearly what was going on. And you can do that by using the reduplication formula that we had before in Theorem 5.1, which I put down here. You'll recall enabled us. I thought of this as a kind of double angle formula. It's called the reduplication formula. I call it double angle formula. Gamma of 2s is gamma of s, gamma s plus a half times this factor. I replace the s with 1 minus s over 2, which gives me that expression. And the point is, of course, we can combine these two together using that other formula we saw that connects it back with the sine function. And plugging that in, that gives me gamma of 1 minus s sine pi on s is equal to this expression. And I can plug all this back into the functional equation, as Riemann did, and the functional equation then becomes this. And if you look at it now, we can start to see some lovely symmetries. We've got pi to the minus s, and this is pi to the minus 1 minus s on 2. We've got a gamma of s on 2, this is 1 minus s on 2, zeta of s, zeta of 1 minus s. And I can put then capital phi of s equal to pi to the minus s on 2 gamma s on 2 zeta of s, and we can turn the functional equation now into something where we can see a little bit more of the symmetries. This function has simple poles at 0 and 1, and to remove these, Riemann wrote psi of s equals a half ss minus 1. This gets rid of the simple poles. The half there is for technical reasons, I think it's to do with the residues, times phi of s. And this gives an entire function now, an entire function psi of s, which satisfies the functional equation psi of s is psi of 1 minus s. And we're going to see that psi, I'll show in a minute, that this psi of s is equal to psi of s bar bar. And that means this thing is real on the line a half plus it. And I'm going to prove that in a second. We'll have a look at that there. So we've turned our zeta function now and the functional equation into a new function. There's psi of s, which I'll write down again in a moment. And this psi of s turns out to be real, at least on the line a half plus it. Now that line, if we look back at our picture again, a half plus it is this line here. And this is sometimes called the critical line. Now, as you'll recall, the Riemann hypothesis says all of the zeros, except for the trivial ones, all lie on this line. And that's the Riemann hypothesis that still remains to be proven. The fact that we now have a function which is real on this line means that we can start to find some of the zeros numerically by simply using, well, firstly, bare hands, the intermediate value theorem, as we'll see. So the so we're going to show that, I'll come back and show that this is real in a second. So it's clear then that in the critical strip, zeta of s is 0 if and only if psi of s is 0, and which requires a little bit of, which is not very hard to see, but it's also clear, which is a little exercise, that psi has any zeros, that if psi has any zeros in the critical strip, then they lie symmetrically about the line sigma's a half. Real part of s is a half. And I'll prove shortly that this psi of s indeed has infinitely many zeros in the critical strip. Now at s is a half, the functional equation collapses trivially, because you just get psi of a half equals psi of a half. Riemann conjectured that in the critical strip, the only zeros are on this line, real part of s is a half. This has never been proven, and as I mentioned, is known as the Riemann hypothesis. Both it and generalizations of it have important ramifications in many branches of mathematics. Hardy proved that zeta of s has infinitely many zeros on the above line, and indeed millions of such zeros have been calculated. And we'll have a bit of a look at that in a moment. Let me just finish off this little page here by going back and showing that if you're on this line, the real part of s is a half, then this psi function is in fact real. Now you can recall from complex analysis that if f is analytic at z, then f of z bar all bar is also analytic. It's just a little result from complex analysis. So if s is real now, psi of s is real. So psi of s then minus psi of s bar all bar is 0, because if this number is real and s is real, then s bar is just the same as s, and the conjugate is exactly the same, so you get 0. So that means this is now 0 on the real axis. And so again I invoke analytic continuation, which says that these must be equal for all z in C. In particular, I'm going to put s is a half plus it in, this important critical line, and plugging that into the functional equation, we get psi of a half plus it is psi of 1 minus that value, which of course is psi of a half minus it, which of course is just a half, which is a half plus it conjugate, and that's then equal to psi of a half plus it all bar. And that tells me then that the conjugate of this so-called complex number is equal to itself, and that only happens when the complex number is in fact real. And so there's a little proof that psi of a half plus it is real. So here's our little picture again, and as I mentioned, I've only shaded part of this. This continues on, of course, above and below. This is called the critical strip, and here is our critical line through here. And as I mentioned before, we've shown there are no zeros over here, there are no zeros over here except at the negative even integers. There are no zeros here. We're going to show shortly there are no zeros here. So the zeros of the Riemann zeta function, there are infinitely many, and they lie in the critical strip, and it is the claim of the Riemann hypothesis that they actually lie on this line. Well, before we come to counting the number of zeros and trying to get some handle on this, I just mention a couple of generalizations of the Riemann zeta function. It's been generalized in lots of different ways. One way, of course, is we've seen before that if you've got a Dirichlet character, then you construct these L functions, which are generalizations of the zeta function. And we've seen before this defines an analytic function for the real part of s bigger than 1. This function also can be analytically continued, and in the case where chi is non-principal character, it leads to another version of the Riemann hypothesis, so-called generalized Riemann hypothesis. Another generalization of this is the so-called Hurwitz zeta function, where in place of 1 on n to the s you get n plus a, so you add another parameter in. So if a is 0, you just get back to the zeta function. This has also been well studied, and again for sigma bigger than 1 this converges. So as you would expect, the results analogous for zeta of s, including a functional equation, can be obtained for this function, and you can look up books on this. It's been well studied. There are other generalizations involving the norms of ideals in number fields. We saw just a little touch of that earlier, where there's a lovely connection between these L functions of L of s and chi and algebraic number fields, in particular ideals and norms of ideals. So the idea there is that you replace the chi of s in the L function by the norm of the ideal, and you take a sum over the ideals, and you end up with generalizations of this, and there's some very deep and beautiful results there, but that is another course in itself. In the next section, we're going to have a look at the number of zeros of zeta of s in the critical strip, and we're going to see that we can prove that there are in fact infinitely many, and we'll find some of these and try and get some asymptotics on how many there are in particular subsections of the critical strip. But I'll leave that to the next section.